So, good day, everybody. Welcome to today's lecture. Lecture 3 in our series. Let's start where we stopped last time. I'm going to share my screen with you as usual and slide over.
I think your audio stopped. Your audio was stubborn, I think.
Okay, let me see.
For me, your audio was just fine. So maybe it's a problem on the other side.
Okay.
Yeah, for me it's also okay.
It's working for most of you. Then maybe you just had some kind of loop in your audio signal.
Yes, it seems like. Sorry.
Okay, no worries. Okay, so, right. Okay, so last time we were talking about broadening mechanisms, and natural line width was the first phenomenon we discussed. Just for you to remember, so last time we said that we are describing this through a damped harmonic oscillation, we said, because we're emitting a photon, so energy is taken out of this oscillating system, and with these ansatz we could derive our line width, which has a shape which we are calling a Lorentzian profile. And today we continue with a broadening mechanism that is much more prominent typically, and is the main broadening effect at higher temperatures and low pressures. So the Doppler broadening is an effect that stems from the Doppler effect that you have if your emitters of radiation are moving, right? So they all have a certain velocity according to the Boltzmann energy distribution, leading to the Maxwell-Boltzmann distribution for the velocities, and therefore you have a certain amount of particles which are moving towards you and some that move away from you. Those that are moving towards you are blue shifted, whereas those that are moving away from you are red shifted. And so you have a certain spectrum or a certain range of wavelength you get even from a discrete emitter due to this effect, because you have a continuous distribution of velocities. Now, how does this translate now in the spectrum itself? If we look at the intensity as a function of frequency, for example, right? So here on this slide, you can see some ensemble of particles, and we come in with some light, for example. Now this is this would be so we excite, and depending if you think now, so if you look at this same thing I just said in the adsorption picture, then you have a source of light coming in. Those particles that move against this light will see a blue shifted light, whereas those that moving in the same direction will see a red shifted light, and therefore also in adsorption you will have this effect of a certain broadening. Now, if the velocity is small compared to the velocity of light, we can stick to the non-relativistic Doppler description, and we can use the formula as it's written here. Nu b is nu naught times 1 plus velocity in the direction of your observation over c. And this connects us now, the frequency with the velocity, and therefore the frequency also with the velocity distribution given by the Maxwell-Boltzmann distribution, which is written here. You can see it's simply a Boltzmann distribution where the energy in the exponent is expressed as the kinetic energy in translation, which is mv squared over 2. And this divided by K Boltzmann and temperature gives you the factor in your exponential expression here. You can also introduce the most probable velocity, which is the square root of 2kt over m, the mass, and write the Maxwell-Boltzmann distribution as it's shown here as the ratio of velocity over most probable velocity in brackets squared. Now, in order to translate this, we just do the following. We have this connection between the velocity v and the frequency nu given through this Doppler relation. And so you can simply do a variable transformation from dv into d nu. So one thing is you transform from v to nu, and then you also have to take into consideration that you transfer from a dv, so an differential in the velocity, into a differential in frequency. So you have to take the derivative dv over d nu times d nu is your dv. And with these transformations, you end up simply with a distribution in frequency space. So you have then a certain probability of finding a frequency, which is then translates into an intensity and has the same shape as we have for velocity. It is a Gaussian type distribution, and we can compare now the line with the shape of this typical profile with the Lorentzian profile. And you see the difference is that the Lorentzian profile has wings that reach a bit further out. So in principle, even if you have a certain Doppler broadening, and you can assume that the Doppler broadening is about 2 orders of magnitude, typically larger than the broadening you have due to natural line width, due to your limited lifetime of your excited state, you have still in the wings information on the actual Lorentzian, and it is possible to some extent to also reconstruct what is buried basically under your Doppler profile. But the big topic, and this is what we're going to address in these next few slides, is how to get rid of Doppler broadening in order to get down to the natural line width. Okay, here's one example given, for example, sodium atoms at 400 Kelvin, and the transition is a relaxation from 3p to 3s. This is a lambda of 589 nanometers, translates into a frequency in the terahertz regime. You can calculate the corresponding broadening. So full width at half max is delta nu d is about 10 to the 9 hertz. So we are in the gigahertz regime here in terms of broadening in comparison to what we had before. If I go back one slide, or maybe two, here was the example. The natural line width of the same transition in the sodium atom 3p in a relaxation down to 3s, you see it's in the range of megahertz. So it's 10 megahertz. So it's about a factor of 100 difference in the actual width. So you can see the natural line width is hidden under a much broader function due to the thermal velocity of your particles that you're looking at. So this is one effect, and the other one that plays a bigger role in situations where you have a higher density of gas is pressure broadening. This stems from collisions between atoms or molecules, so colliding particles, which have an effect that is similar to simply shortening the actual lifetime of your excited state, because due to collisions, you change the probability for a transition, for relaxation processes in general, and you can find a corrected expression for the lifetime and therefore for the broadening, which is consisting of two contributions. One is the natural line width, here in frequency range expressed as nu natural, which is 1 over tau, the lifetime, plus another term, and this term stems from the collision probability that you have, which is higher the higher your density is. You can write this as so this has a unit of a frequency, it's unfortunately written as an omega, so it's looking like an angular velocity. But here, I think I've taken this from Hertel-Schulz. It's supposed to be a frequency, or at least something in the unit of hertz. And you can derive this as a product of a few ingredients, namely the particle density multiplied with the cross section, which is here written as a sigma, and times v, which is the most probable velocity that you have at a given temperature. And again, with our Maxwell-Boltzmann distribution, we can link this to a given temperature. And with these values, you can estimate this frequency contribution. And if you add it to 1 over natural lifetime, which is again a frequency, you get some frequency multiplied by h bar gives you an energy. So this will tell you your line width in the unit of energy, written here as uppercase gamma. One last thing. So here it's given again for sodium atoms at room temperature and our standard atmospheric pressure. So we have 1 bar, and you get something in the range of 5 or 6 times 10 to the 8 hertz in comparison to what we had before. So another way of distinguishing between these contributions is to speak of homogeneous and inhomogeneous types of broadening. This is a little bit misleading because it doesn't say what this homogeneity is referring to. It means simply with respect to atoms. Are the atoms, can you distinguish between them due to this broadening effect? So are different or are the atoms affected in different ways by this broadening mechanism? And this is the case only for the Doppler type broadening, because in principle each atom has a certain value of velocity and is therefore with respect to this velocity distinguishable, and therefore this is an inhomogeneous type of broadening, whereas the other two effects, they are the same for all the atoms in your ensemble, because it's the same internal excitation that you're looking at that has a given lifespan and a certain natural line width because of this. And the second, the pressure broadening, so a statistical effect. So it's an effect that could you please check your microphone and switch them off? I'm afraid somebody has the microphone.
Christoph Mülleder, I think, yeah.
Yeah, sorry, I noticed it just right now.
Okay, thank you. No worries. It's just if there are so many, it's hard for me to do it myself. Thank you. All right. Okay. So right. So this is another way of distinguishing. You can say there are homogeneous types, and there is this one inhomogeneous type, the Doppler broadening, because it depends on velocity. And this is the one effect that we would like to reduce, because it has in our typical experimental conditions the strongest influence and the largest broadening that we can see. So we can say our actual natural line width is sitting somewhere under this peak, and this is just repeating what I said before, so I can just skip this slide here, and we come to solutions how to perform a Doppler-free spectroscopy. And the first one and the most straightforward way of reducing broadening effects is through collimated atomic beams. And you can see here on the right-hand side of this slide a setup where we have some heating chamber which is filled with the desired element. For example, if it's an oven filled with some for example, because we were talking about sodium, let's suppose it's some alkali metal, and then you heat it up. So you have some vapor pressure building up, and you have a slight nozzle, an exit point where this heated gas can expand through. And this is now like a point source spreading out in all directions. And now you use a system of apertures to cut out a regime or a range where the particles have a very small component in their velocity in projection onto the laser beam, which crosses our molecular or atomic beam at 90 degrees. So this is the idea. We come in with a laser beam at 90 degrees and we try to keep our projection of the average velocity onto this laser beam at a minimum value. This can be achieved simply through cutting out a small region, because you have a spherical angle, and therefore if you have a certain arrangement of slits here, you can cut this out. However, you do this obviously at the cost of what? What's the, this is a straightforward way of doing it, but it will cost you particles. Yes, it costs you particles, and therefore it will cost you intensity in the signal, because it's only a few particles that remain. You can do spectroscopy on the remaining, which is significantly Doppler reduced, but you have surely much less signal. Okay, here on the left-hand side, I also added a quick, more or less unrelated reminder, the Brewster angle and its application. Because when you look at the laser that's coming in here from the left-hand side, the laser is going into a UHV setup, because of course here in this part we have the heating chamber where we create some significant vapor pressure through the heating, and then we expand into a near into vacuum, basically, more or less. You can also improve by having a staged series of pumps with increasing levels of or increasing quality of vacuum. So here, in the end, it's a UHV setup. So we are at very, very low pressures and have basically particle trajectories without collision, which are much, much longer than the actual length of your setup. So this is a true molecular beam without any collisions in the gas phase anymore. And so this is now completely pumped, and so the laser has to pass through a window here, and this window is cut in a Brewster angle in order to avoid any reflection. You want to get as much of the laser intensity as you have, as much as possible into your machine, and therefore you cut this in the Brewster angle. How is the Brewster angle defined? You can see we speak of the Brewster angle as this angle here in the incoming beam with respect to this line here, which is perpendicular to the surface. This is how we define angles in optics. So this is the Brewster angle, and it is the angle where the reflective or the reflected and the transmitted beam have an angle of 90 degrees. Now, what's so interesting about the Brewster angle is that you can use this now because of the following thought. If you look at this point where we make the transition from, say, air into gas, or glass, actually, in our case, right? So this is the glass window. We go and have this transition at this point. And if we are coming in at the Brewster angle, then this and this vector here are perpendicular to each other, which means if there is intensity in both of them, then how would you say does the dipole have to be arranged? So in which direction is the dipole oscillating in order to have intensity here and here at the same time?
The Z direction in the plane to the screen. pointing
Exactly.
outward.
Yeah. So right. So the dipole has to be oscillating along a vector which is in projection right now when we look at the paper plane. So it's coming out and going into the screen plane. This would be an oscillation that allows an intensity in this and in this direction. Why is that? You just have to think of the dipole characteristics and look at how intensity is distributed in this case. You have these lobes. I probably take you quickly to. So yeah, I have. If this is the direction of how your dipole oscillates, then this would be the intensity distribution in space. And you can see there is zero intensity in this direction. So if it's oscillating like this, you have the possibility to also be exactly in 90 degrees angle with intensity. And so our dipole on the screen is coming out of this screen plane. This arrangement would allow for intensity in both directions. Now, you can say, now if I come in with a light that has a certain polarization, so it is oscillating in a given plane, then you only have an intensity here and here if the incoming plane, this vector that you're oscillating in, has a projection onto the direction that we said is set or in projection coming out of the paper plane, right? So only this component of your vector has the ability to radiate at this reflective direction and the transmitted direction at the same time. In other words, if I'm choosing a polarization in the paper plane, which is indicated by the red arrows, I have zero projection onto the dipole oscillating in a way to fulfill the conditions for intensity here and here. And therefore, this type of polarization will be only in transmission. It has to go through in transmission, and it cannot be reflected, because you can also think of it this way. If the light comes in this arrangement, you are creating an oscillator in this direction, right? And if it's oscillating in this direction exactly along your direction of the reflected beam of light, no intensity can be emitted in this direction, and therefore everything goes through. So you choose the polarization of your incoming light as it's shown here in red, and then you can be sure that all of the light that you shine onto your glass plate will go through and nothing is reflected. So you're minimizing your loss through reflection. Okay, so this is just to for you to remember or to make this link with optics lectures you heard before. Okay, so what's the outcome now? This is again a schematics where we have some gas or some, think of it as, for example, an alkali metal liquid here, because we heat it, and then you have some vapor pressure and you let it exit here. You can take advantage of certain additional effect. It's not just the fact that you have a point source where you have the beams, or basically the trajectories of the particles coming out in all directions. You also have effects that stem from interactions between these particles. You might even have a type of phase transition in your material through expansion. If you think about a gas expanding into vacuum, like in the Linde technique or the Linde approach, where you expand into vacuum at the cost of inner energy, then the gas cools down. If you are under the inversion temperature, you can use this to create, for example, in our labs here at the Institute of Experimental Physics, the expansion of helium through a cold nozzle causes the helium to coagulate and form small droplets, for example, to do studies in superfluid helium nanodroplets. So that's one special technique of spectroscopy, which has some other advantages. I think you will hear a little bit about this later. But in principle, what you have is you have a certain distribution of velocities of particles given or determined by the conditions of pressure and temperature on both sides of your nozzle. And you would like to end up with a situation where you transform most of the thermally distributed energy in your degrees of translation into just one degree of freedom, the translation into, for example, the Z direction, which is, so to speak, perpendicular to the aperture you've chosen here. So if this was your original distribution of velocity in the Z direction, then you have, after setting up this nozzle and aperture combination, a much sharper distribution of velocities around some average exit velocity for your gas particles. And now, if you can think of it this way, if you are sitting on one of these particles moving at the velocity u, then your actual thermal distribution has to be measured with respect to this constant velocity u you're moving, and you see then that the variation of velocities in this direction is much smaller. So your width of this distribution is much smaller compared to the width of the distribution you had before, where it was the full thermal average overall degrees of freedom. So we take advantage of this and do spectroscopy now on this collimated beam with an excitation and that comes in perpendicular to the velocity of the molecular beam. And a very obvious demonstration of these effects is given here. If you compare figure A and figure B, it's a spectrum of NO2 at the temperature of 300 Kelvin. In case A, just the adsorption spectrum at 300 Kelvin, and then the same thing measured in a supersonic beam where we use a carrier gas as well. So what you do is you have a diluted amount of NO2 molecules in a inert gas, so that you don't have any chemical type of interaction between the two gases that you mix, and you let this expand. So you build up you have a big pressure difference, several bars of pressure inside. You expand into vacuum. You have this effect of cooling. You have this collimation, and even in this, if it's for example such a big difference in pressures, it's a so-called supersonic expansion, which has an even sharper type of distribution of velocities with respect to angle. And from this distribution, you even cut out just the most the part which is closest to the z-axis, to really just look at those particles that have almost all the same velocity in direction z, and very small broadening of the spectrum in this direction, and you have a almost negligible component of velocities in directions perpendicular as well to the beam of light that does the excitation, right? So you have in the end the improvement from A to B. You see in A, for this NO2 spectrum, you can not resolve rotational transitions in the molecule, whereas if you do spectroscopy in this supersonic beam. You say it's sometimes a seeded inert gas seeded experiment. So you have this super sonic beam consisting of the carrier gas and the gas you're interested in. In the case of NO2, you see in this range between 1600, 600 and 1600, 900, you have a rotationally resolved spectrum in comparison to what you have if you do a direct measurement, for example, in this chamber here at 300K.
Sorry, I have a question to that.
Hmm?
I have a question to that. Do you change the population of certain states when you change the velocity, for example, or the pressure of a certain gas? And does this have an influence on the transition probability in respect to when you do it with a natural gas at a certain pressure?
You will have changes in intensities for the frequencies that you measure, simply because the occupation of the levels that you are looking is a function of temperature, right? Because any internal degree of your molecule will be more or less populated given through your Boltzmann statistics. And therefore you're right. So this, depending on the temperature, you will have different intensities in the spectra. But since it's a discrete type of spectral situation determined by how these levels are arranged, you don't have a shift in frequency. This is true in the ideal case. However, you also might have some effects through interactions. For example, I can give you an example of research done here at the Institute. If you think about embedding particles into superfluid helium nanodroplets, you pick the helium obviously because it has this inert character. Helium has these 2 electrons in the 1s shell. It is not interested in studying any type of chemical interaction. However, it does affect, to some extent, it does interact with the molecule that is sitting, for example, on or inside of a helium droplet. There is always a certain type of interaction that simply stems from mutual polarization effects between atoms or between molecules. We call them the van der Waals forces. And therefore, due to this interaction, you have a coupling of your degree of freedom in this molecule that you're looking at. For example, it is a vibration of a molecule somewhere sitting on the helium, and this vibration will be talking to the helium, and therefore you also have a broadening effect. And another effect, it also shifts the resonance frequency for this molecule. So there is a slight shift also involved if this material or if this seeding gas that you're using interacts in some way with the material that you were investigating. But typically for a standard setup where you do a spectroscopy on a supersonic beam, there is no shift in the frequencies, but a change of intensities according to the temperature that you choose for your heating chamber. Yeah. Okay.
Sorry. So if you just speed the particle up, let's say it's a pure substance without any other substances, and you speed the particle up, doesn't that influence the rotational states, for example, that certain rotational or vibrational states are now not as suitable than before, or is that completely non-interacting?
Yeah, no, you can. So here the translational degree of freedom does not couple onto any other degree of freedom that you look at in your molecule, unless you look at the effect that something that has higher energy might, in terms of translation, might have also a higher collision energy between particles. Right. So this is then some way where the momentum that you have in one direction might translate into energy transfer into some other degree of freedom. But there is no direct coupling of the translation onto rotation, vibration, and electronic excitation. So in principle, if you look at the molecular system, you are translationally invariant. It doesn't matter how fast this system is moving. It has the same energies in electronic excitation, in vibration, and in rotation. But you're right that in principle, if there is already some energy in some degree of freedom, and you account for a mechanism that couples between them, for example, a collision, then obviously higher velocity with a certain probability of colliding between these particles will also translate into a different distribution of energies in these other degrees of freedom, and will change the intensities in these lines due to this coupling mechanism. But it does not touch the actual frequencies and therefore the internal states in rotation, vibration, and electronic excitation. Okay, so this is the first solution, basically collimated beams. Here's an example from Hertel Schulz, where they show this oven and the skimmer, which is this cutting out. You have this nozzle, and then you cut out in some inner region of your distribution, of your angular distribution. You cut out, and then this is what you have as the remaining beam. So here they give it they speak of a delta theta, which is the variation in the angle, obviously dependent on the choice of your aperture width here. And they compare two things. So this is an experiment that is mainly just demonstrating what happens if you are doing the experiment worse than you can do, namely in one, and this is the most reasonable setup. In one case, you go in with a laser perpendicular to the beam of light. And the other one is where you come in with a laser that has an angle. So there is some component of velocity that gives a big Doppler effect, obviously, because the light's coming in like this. So there is a certain component of the velocity that is going directly into the direction of the incoming light or away from it in so relatively thought. So you have two different spectra that you can record. The example system here is the sodium atom, and we look at the transition from the 3p3/2 to the 3s1/2 state. So maybe we should also take this as an opportunity to reactivate our knowledge of atomic physics. So it's a p to s transition. So P means we are talking about the angular momentum of the electron hull. If it's P, then L is equal to 1. Then 3p and 3s, 3 itself is just the principal quantum number, so our n in the typical nomenclature from quantum mechanics. And then we have this 3/2 and 1/2. Does anybody know what this means?
Magnetic number, the set orientation of our angular momentum.
It's not the magnetic number, no, but it is something that couples two things. What is coupled here?
Our spin, maybe.
Yes, yes.
Wow.
It's the spin, and what's the spin of a sodium atom? What's the total spin of a sodium atom?
Well, this is it's charge number is 3. The charge number 3 of sodium.
The charge doesn't really help you, but the position in the periodic table is helping you, because
That's the thing what I'm trying to use in that sense. If I know if it's the charge to 3, then I know it has 3 electrons.
Yeah, it has more than 3. I will show you. Let's open the.
Ah,
You're in the wrong row. You're right in what you're thinking, but you're in the wrong row. I'll show you atomic. So you said 3. 3 would be lithium, and the next one is sodium. So you were right in your thought that we are here with talking about alkali metals, meaning that we have a situation where we are having a single electron in the valence shell, and this valence shell is an S shell, right? So these are elements that have a single electron in the S shell. For sodium, we're in the third. So it's N equals 3, L equals 0 in the ground state. And we have only one electron, which is unpaired. excuse me, with just one electron which is unpaired, and therefore our total spin is what?
Just 1/2.
Just 1/2, exactly. So if I go back to the slides, you can now calculate the possible coupled momentum. So you call it the angular momentum of the electron hull, or the total angular momentum of the electron hull, which consists of your angular momentum of the hull, of the valence shell, plus your spin. And in an S state, L is 0, so your total J, that's how it's called, is 1. And here L is 1, so your total J can be, for example, 1 plus 1/2, giving you J equals 3/2. And so in order to see light coming from here to here, it must be a transition that is dipole allowed. And there are some selection rules that boil down to simply symmetry of the wave functions involved in this process. And in this case, the rule is that delta J is plus minus 1, and delta L has to be plus minus 1 for it to be optically allowed. And this is the case for these transitions from P 3/2 to S 1/2. So you see these two transitions. And in this example here, it's just showing you, so this would be the situation, almost nothing here and a little bit here, for the situation where you come in with a beam like this. And if you come in with the beam perpendicular, with the laser perpendicular to the beam, you get these two peaks, and the separation between this peak and this one is 1.77 gigahertz. So here they write about the 1700 megahertz. It's the difference between these two states, because you can see this transition and this transition. Now, why do we have two states here? What I was talking about here is simply fine structure. And what's coming in here when we speak of hyperfine effects, which other degree of freedom is accessible in principle in this atom that we haven't talked about yet? There's another piece that has a spin.
It's spin-orbit coupling.
This is already, so this is the spin-orbit coupling is what goes into this quantum number J here, because it boils down to us reintroducing or introducing an angular momentum quantum number for the coupled angular momentum stemming from the spin and the actual angular momentum of the electron. So J is already the angular momentum. So this is your spin orbit coupling term. But then even in this spin orbit corrected expression here, where we have the 3s 1/2 state. So it's clear how L and S are arranged, because this gives you a certain J, right? So, I mean, in this case, it's very trivial because L is 0. So there is only one value for J, because 0 plus 1/2 is 1/2. So this is already taken into account and leads to fine structure. But hyperfine comes in if you introduce yet another spin. Which spin could that be?
Maybe the nucleus?
The nuclear spin, right? So if we introduce the nuclear spin, or if we have sufficient resolution, we can also see an energy change with respect to how the nuclear spin is arranged in the field created by the oscillating, or by the electron hull, basically. Okay, so you can see it this way. You have this certain electron distribution. This creates a field at the position of the nucleus. And if the nucleus has a magnetic dipole moment, and this magnetic dipole will arrange in the field that we create, and therefore introduce yet another energy splitting. And this is what we see here in the 3s 1/2 states. And the difference here, the splitting, is about 1.7 gigahertz. And you can see this very clearly only if you go in with a laser perpendicular to the beam, because nobody would come in like this. This is just to show you the effect of a Doppler broadening, which could have been avoided. Okay, so these are This is the first method. The second method of Doppler-free spectroscopy is a method you apply in cases where you have molecules or particles that are ionized. Because if they are ionized, you have another handle to work with your matter. You can influence it by having a electric field, obviously. So, and here interestingly, you do the following. You have a laser that is now parallel to the acceleration you cause by having your charged particles move in this field between two electrodes. So suppose we have a positively charged particle here. So we have taken off an electron through some process, and we have a positive electrode here. Then we have a repulsion and an acceleration of this charge towards this other ring here. And if the potential difference between these two rings is U, our voltage, then if it's singly charged, then it's simply the elementary charge times U, which gives us the energy, the potential energy that our particle is falling through, which directly translates into increase of velocity. So we have this potential energy, E times U, directly translated into kinetic energy, mv squared half. We can solve this for the velocity and have a velocity expression as a function of the actual energy, W, and W is this product of charge and potential. Now, while we're doing this, the trick goes now as follows. If you look at the Doppler shift again, the Doppler shift of the applied laser frequency, it's written here as nu L. So this is the frequency, or the, if you translate it into a wavelength, a certain wavelength of the laser you use for excitation. And the Doppler shift that you have due to the fact that the particles are moving is in first order proportional to V over C. This is a fancy way of saying the same thing that we had before. I'm just going back a few slides quickly. It's exactly this type of formula, which is valid in the case of small velocities in comparison to speed of light. Otherwise, you would have to swap to the relativistic description of the Doppler effect. But so in first order proportional to V over C. So you can say 1 plus V over C in brackets times nu gives you your delta nu, your change in frequency. Why is this relevant? Well, this is shown here. Now, the trick is that you can assume that the distribution of kinetic energy, we write this distribution, so we have some probability of finding particles with a certain velocity, and therefore we have another distribution of particles with a certain kinetic energy, because they are linked through the square, but not the same, because they are linked through the square, a certain distribution of kinetic energies. We call this distribution as a delta W. You see, it's to indicate that we are speaking about a certain variation and not a direct derivative. It's this other type of delta that's chosen here. I've taken this from Hertel and Schulz. If you're interested, you can read it up in more detail. And now with this knowledge, we can do the following. We can say a distribution of velocities, so this is written as this fancy delta V, is now the derivative of your expression for the velocity as a function of the energy, derivative with respect to the energy, times your variation or your distribution in the energy, right? So you can simply translate the distribution in energy into a distribution in velocities. And this is the interesting thing, because since it's connected through the root, the square root, if you take the derivative with respect to W, you get 1 over 2 times the root expression times the inner derivative times, and here comes the delta V, the distribution in velocity. You see the distribution of, the distribution in energy. So you see the distribution in velocity and the distribution in energy are proportional to each other times, and then comes the factor where the energy comes in under the root, one over the root of the energy. So one last step to translate now the distribution in velocity into a distribution in frequency. We use the Doppler relation that we have written, or that's written here. Yeah, this expression here can be used to translate now our distribution in velocity into a distribution in frequency. And we have nu laser times variation in velocity over c. And therefore you can see this translates directly into this relation. The distribution of frequencies is the distribution in energy expression, but divided by something that is proportional to the square root of the actual energy. And this means that if you increase the energy, or in other words, if you put a very high voltage on these rings and have a strong acceleration, you effectively reduce the broadening effect, because you are measuring because you can assume that the kinetic energy distribution stays the same, but you are now looking at an ensemble of particles which are moving effectively at a much, much higher speed in this direction set in which you accelerate. So you can use this effect to do Doppler-free spectroscopy, because you can reduce the broadening that you see here effectively simply by going to very high acceleration energies or high field, so that you have a very high velocity in the z direction and therefore a reduced delta nu. Another thing as a side comment that you can do here is you can actually use a setup like this for charged particles to do spectroscopy with a laser that is not tunable. So, or if you're not able to tune any finer with your laser, you can adjust. Basically, you can now use the Doppler effect to adjust the resonance, to adjust your effective energy of the photons when hitting the particles to their internal resonance by giving them a certain velocity, right? So this is just a side comment, but this is also something that has been done. You use this type of setup to, instead of going through different wavelength on the laser excitation side, you simply shoot particles at different velocities in a way where you can nicely control the velocity through a setup as it's shown here, because you have a well-defined kinetic energy that you give this system through acceleration of the charges in a given field. This is solution 2 and works in cases of charged particles.
In this case, we really are measuring along the acceleration lines.
Yes.
Not along.
Yes. Okay, now comes solution 3. This opens up a new field of spectroscopy, which is called saturation spectroscopy. And it is based on an effect that makes or deviates from a first assumption that you typically make when thinking about light absorption. You describe it typically through the Beer-Lambert law, which is derived from a simple assumption that is written here in differential form. You say that the amount of adsorbed intensity is proportional to the incoming intensity at a given depth of your material times some adsorption coefficient and times the thickness. So your intensity will decrease obviously with the thickness, but it will also increase with respect to the amount of intensity that is still present at a certain depth in the material. And these types of relations always lead to an exponential law, which you can see immediately by solving this differential equation, putting the I on the other side, and then integrating on both sides. You get the Beer-Lambert description for the intensity as a function of the depth. So if you shine light on some matter, then you have an exponential decrease of this original intensity of incoming wave with respect to the depth in this piece of matter. Now, this is called the linear range. It's called the linear range because your infinite amount of adsorption is basically proportional to the intensity at your given position in this piece of matter. But if you just have a system as simple as a two-niveau system where you have two levels, you will deviate at some point from this approximation, because the intensity you shine on some light, you provide a certain amount of photons per time, per area, will change the occupation, or will change the population, as we say, of your ground and your excited state. If you are in a certain range, or if you are in this resonant area, or if you have if you're offering light with a frequency which is a resonance frequency of your quantum system, then you will induce a excitation from the ground into the excited state. And this, however, means that less and less of the atoms in this piece of matter will be in the ground state and are accessible to your photon excitation. That means that if you reach a certain amount, or if you have a certain intensity, you will have saturated your piece of matter, because all the electrons that have been, or that had been sitting in this ground state are already excited, and you still have more photons to excite, but there is nothing that can be excited anymore. So obviously these photons are left over. And this means that at some point, if the intensity is high enough, you saturate, and your transmission you will have light also transmitted through this object, because you have saturated all possible adsorbers in this piece of matter. In the two-niveau system, it looks like this. You can say that your change of intensity is the incoming intensity times some cross-section for the adsorption to take place. And then comes the difference between your initial number of initial state atoms, so the atoms that can be excited, minus the number of electrons or particles, let's say it this way, number of particles in the excited state. And if the intensity is high enough, then Nk, the number of particles in the excited states, is the same as the number of atoms that have been in the that have been accessible in principle or in the ground state before, right? So in this case, you have zero change in intensity anymore, meaning that all possible adsorbers are saturated because they are in an excited state, and you do not have any loss of intensity anymore. And this state is called the nonlinear range, the saturated range. Obviously, this is only the case if you have sufficiently high photon densities. And this field of optics is very interesting because it creates many new effects. You can if you're interested in this field, I recommend the lectures of Professor Krenn or Professor Koch, for example, where they are showing you several devices which take advantage of nonlinear optics, for example, for frequency doubling in certain materials, and so on. So this is a very fruitful finding that can be used for many applications in spectroscopy. And here we are going to use it to reduce our Doppler broadening. How is this possible? On this slide, you can see the basic principle. What happens if you have a certain piece of matter, or you have some cell filled with a gas? Let's think of it as a cell filled of gas, because you have some temperature and therefore some broadening. So this is Doppler broadened. We have some resonance frequency. And if you look at the signal in transmission, when going through a certain range of frequencies, meaning you have a source of light where you can go through, where you can tune through, you will see that at first you have maximum transmission, and then in the area where you are resonant with your quantum system, you have a reduced transmission, because now you have a lot of absorption. And then if you are going away from your resonance, then of course the transmission will go up. You can also think of it in terms of population, that you say, okay, the moment I'm getting in the range of X of resonance with my excitation from the initial to the final state, I will start to populate the final state. Okay, this is the first thing. This is obviously what we observe. Now we do something else. We have this laser go through this frequency range, but at the same time, we take a second laser and park it at some fixed frequency. What's going to happen? So if the laser is sitting somewhere, and you take the second laser and you go through this spectral range here in this area of frequencies here, there will be a point where you cross, or you have the same frequency as this fixed laser. And if this fixed laser has sufficiently high intensity, then this laser will have already excited all possible excitations with this all atoms so will have excited from the ground state to the final state for this resonance with this frequency. And therefore, if your second laser, when tuning through, passes here, it will hit an energy range where this other laser has already populated the excited states. And therefore, there is nothing left for the tunable laser to populate. And the photons that you offer are going through. So you have a slight increase in transmission, because the other laser has already depopulated the ground state that you wanted to excite with your tunable laser. So you see the dip where the other laser is parked. You see the dip in transmission, or you can also think of it as population. So the population of excitable levels in a given frequency range has dropped at this frequency where the other laser is already pumping into some excited state. So these are no longer accessible because they are already excited. Therefore, their population, the population of these ground state levels that can be pumped through the laser, they are this is no longer accessible because they are already pumped by the other laser. So this is why you have in population this slight dip. It's also sometimes called a hole in the population distribution. I think it has a name, I think Bennett hole in older literature. So this is something that you simply see by parking one laser with sufficient intensity and then scanning through with the second laser. So the question is now, how are we going to use this to do Doppler-free spectroscopy? And the answer is this graph. You take two lasers, or even better, you take one laser and you split this laser through a beam splitter. This could be a piece of glass with a suitable coating. You don't split it 50-50 in intensity. You split it into a very, very large intensity and a smaller intensity. The one with the big intensity is what you call the pump laser. It has to have big, so high intensity, high density of photons, because this beam is supposed to saturate. And the other laser, or the other part of your split laser is the probe laser. And now you split them up here. You go left with the probe laser, you go right with the pump laser, and both of them are going now through your adsorption cell, but from opposite direction. The angle between these two is just, I took this, so this is from Hertel Schulz, I think, a graphics, but you can find it by now in several textbooks. It's a standard way of explaining this saturation spectroscopy phenomenon or this technique. So you come in like this with the probe laser, and you come in like this with dashed line with your pump laser, and this angle is basically zero. It's just, to see what's going on in this graphics, it's a little bit open. But in principle, they're exactly opposite to each other, so they have an angle of 180 degrees. And now I am tuning through the range where I assume that there will be a resonance of my molecular system or of my atomic system. Okay? This lock-in, we'll talk a bit later. For now, just think about these two lasers coming in from opposite directions. And now I show you what you see. You see a signal. Let's look at it in transmission. You see, the closer you get to the resonance frequency, the less transmission you will have for your. So there was just a question, why is the pump laser pulsed? I'll get to this in a second. First, we have to understand why we arranged them in opposite directions. So the pump laser and the probe laser are scanning through this range where you assume some structure, and they are tuned together because they are basically the same laser. And now if you look at the transmission as a function of frequency, in the area where you are in resonance, you have a reduced transmission. But then all of a sudden, at the very middle, exactly where you have the natural, or where you have your exact transition, there will be a slight dip. And this dip is the exact position of your resonance in this atom. My question for you is, how is this possible? So let's go back here. How is it possible? Why do we see this little dip at the moment of the real resonance in the system? Anybody?
Maybe the idea, I haven't completely formulated it in my head, but both lasers, if I have a particle that moves from the right, example, then one of the lasers will have a shift to the blue spectrum, the other one to the right spectrum.
Yes.
So they do not really interfere with the saturation because we're exciting different kinds of particles.
Exactly.
The only exception is the one that is at rest. So the one with the zero velocity in both directions. So we have no Doppler. If we're looking at this one particular, this has no Doppler bias.
Exactly. This is exactly how I would formulate it, right? So only those particles in this velocity group of v equals 0 are feeling both lasers at the same time. And only for this group of particles, you will have the effect of saturation. Because in all other cases, the saturation laser and the probe laser will see shifted frequencies in opposite directions because they come from opposite directions. So if a particle is moving with some velocity to the left, in our example, then the probe laser would see it blue shifted and the pump laser would see it red shifted. So they cannot interfere. So what happens is that only for this velocity group with v equals 0, and this is the one that gives you the correct unperturbed Doppler-free resonance, you can see this dip. And now with this, we come to the question, what is happening here with the chopper? The chopper is something that cuts your pump laser into little portions. So you have a chopper. It could be simply an aperture or some like a circle with a small slit, and it is an electromotor that turns it with a certain frequency, right? So you chop or you modulate your signal of the pump laser. And this means that basically you are switching on and off the pumping. And only if you pump, you saturate. So you can compare the signal where the pump laser is active to the signal where the pump laser is down, because it's blocked by a wing of this chopper here. And by taking the difference, you get a differential signal. And this is shown here as a signal. See? So you get the difference of transmission with and without the chopper blocking the pump beam. And this is the signal that you obtain. And with this signal, or this is what this still has some line width, but this is then what remains, because you're now with the particles that have velocity 0, and it is the natural line width that is basically what's left here in your signal. This is the idea. This is Doppler-free spectroscopy through the nonlinear effect of saturation. An example is given here. I also picked it because it's supposed to reactivate our knowledge of atomic physics again. It shows us the Balmer line in hydrogen. So what's going on? We have here a comparison of theories that describe the energies of the electron in the field of the nucleus for the system of a single electron in the field of a nucleus. We can solve it on the paper analytically. We set up the time-independent Schrödinger equation and solve this equation through a separation in an angular and a radial part, and we get a solution. If we compare the Schrödinger solution to the solution offered by Bohr in the Bohr model, which was this two-dimensional model where we think of the de Broglie wavelength being bent around some circular trajectory, all of a sudden it turns out that Schrödinger gives also just the same dependence in terms of the principal quantum number. And so one has to dig a little deeper and introduce spin orbit coupling. We go and take relativistic effects into our expression and switch to the description by Dirac. So at first we have what we end up with is we see that we have a energy dependence not just on n, but also on J, where J is the coupling of L and S, with L being the angular momentum of the electron hull and S being the spin. So you have J3½ here and J1½ in this system of the hydrogen line. And then comes, if you have sufficient resolution, you can even discover a much finer energy difference when looking at this level with J equals 1/2, because you have the effect of the lamp shift, which can only be explained through the quantization also of your electric field. So you need quantum electrodynamics to do it properly, and end up with a splitting of the J equals 1/2 state into a state which is a duplet S 1/2 and a duplet pi 1/2 state. So this energy difference is very, very small. It's 0.035 wave numbers. And I'm telling this story. I'm telling this story because you cannot resolve this lamp shift without correcting for Doppler broadening. And this is shown here. You can see the levels in this abstract way where we just plot energy in the y-axis here, and we give names to the levels. We have the 2p1/2 and the 2s1/2. So this is the splitting that we are interested in, and we can only see it because of symmetry constraints, which translates into so-called selection rules. The selection rules are delta J equals ±1 and delta L ±1. So you can see from 3p1/2 you can go down to 3s1/2, and from 3s1/2 you can go down to 2p. Let me see. From 3s to 2p. So you have these lines here and these lines here, and you get a certain broadening at first if you look at the actual spectrum in your measurement, if you don't correct for Doppler effect. And the moment you do a Doppler free spectroscopy, you can see these lines very nicely, so as peaks, as it's indicated here. And my question for you is the following. There is something written here as crossover resonance. So you can see here a peak for example, 2p1/2 and 3d3/2. Here you can see s1/2 and p3/2 and so on. This would be p2/2 to 3 1/2, I think. So you can see these peaks here, and then in between you have the crossover or resonance. What could that be? What could be the reason for these unphysical extra peaks in your spectrum? Does anybody have an idea? What could be the reason for that?
It is correlated with crossover resonance. Which transition is this here in the above graph?
So there is no real transition.
Oh, okay.
It is a fake transition that only appears as a peak due to an effect that has to do with the way how we are doing it. We have to go back to this picture. What can happen as well? I give you a hint. You don't have a single resonance in your system. You have typically several states which are more or less which are close to each other, and so there is something that can happen. So what could be a possible scenario that gives rise to a fake peak? We said that here, in the case where it's just one resonance, the system is only, or the pump and the probe laser are only interacting in the case of the velocity group V equals 0. But if you have a second resonance in your system, what can happen?
So that one is just exacting the one that just shifted halfway in the other one, in the one direction. So the particles move slowly in one direction and slowly in the other one. So that the one laser is exciting the other one. So they just, it's not perfectly matching. You're on the right track. It is basically this. So if you have a second resonance in your system, then it can happen that you are hitting a velocity group which is non-zero, but for this velocity group, a right-shifted or a blue-shifted resonance of type 1 fits a red-shifted resonance of type 2. So they can just, meet each other in the middle for some velocity group, because you are offering particles that have all kinds of velocities. If it's just one resonance frequency in the system, then it's only this velocity V equals 0 that can interact. But if you have two resonances in the system, then one is higher in energy and one is lower in energy. And the one that's higher in energy might be blue shifted in some, might be red shifted in some group, yeah, in the velocity group that is moving, so to speak, away, or is not moving towards, but with the laser, right? So then you have this redshifted, and at the same time, it's also blue shifting the other resonance, which is actually low in energy, but for some group, these two will meet. And then accidentally, you will have another resonance peak just because of this effect. And these are the peaks that you can see here in between. This is just a thing that you have to deal with. It's not a big problem because it is obvious from the main peaks where these resonances have to be found, because this is simply dependent on your difference in energy between the two real excitations or resonances that you can find in your molecular system.
I'm not completely 100% convinced actually how this now works, because you have two different frequencies that hit this specific group of atoms. They get two different frequencies. So what is the saturation? Do we just mean that there are no, because of the pump laser, for example, we put them in the higher level, for example, because in this blue shifted, and then we have no.
So yeah, you're right. I forgot to. There's one thing I have to explain. If you think about changes in population, then these two levels can only communicate with each other if they are excited from the same ground state.
Okay, good.
Yeah.
Okay, so this is just it that we say because the frequency, our pump laser depletes this specific velocity regions in that sense, which we could use for the other laser in the redshift to put it in the lower energy.
Right.
That's it. Okay.
Yeah.
Okay.
Yeah. Thanks for reminding. This is actually an important point for understanding. So you have to have levels that share the same ground state, because then you dig off, you depopulate, as you say, the ground state, which would be also the starting point for the excitation with the other laser. So this is how they are coupled, and this is where this resonance has its origin. Thank you. Okay, so this was type 3, and now we come to the last type that I wanted to discuss. Solution number 4 is 2-photon spectroscopy. This is conceptually pretty easy. So what you do is you could just come in with, you split your laser and you come in with it from opposite sides. And what's the gain now? If the particles are moving to the left or to the right, they will see, for example, if they move to the left, they will see the light coming from the left blue shifted and the light coming from the right red shifted, but in the same amount. So this is always a compensating effect. The energy missing, so to speak, due to the redshift is the energy gained due to the blue shift. And so in 2-photon adsorption, if they come in from opposite effects, you have the great advantage that independent of the actual velocity of your particles, you are always in resonance only if you're offering exactly the right frequency for this transition. So you're always Doppler free. So that sounds like a great deal, and it would be if there wasn't a catch to this. And the catch is that the probability for this process is very small. Why? It's on the next slide, but it's clear that the probability for a absorption of a photon, when the probability for absorption of one photon is p, then the probability for a 2-photon absorption is p squared, and therefore you need a very, very high intensity in order to have this phenomenon or this event to occur often enough so that you get reasonable spectroscopy, or so to get a reasonable intensity for this excitation. But the good thing is that you do it with the whole mass of particles independent of their velocity due to this cancellation effect in blue and redshift. Unfortunately, there is yet another catch to this method, because there is a difference in what you can actually excite in a 2-photon process compared to a single photon process. Why? What's your guess?
double the energy?
Well, the energy matching has to be that the sum of the two photons in total must be exactly the resonance of this transition you have in the system, right? Because you kind of lifting, you can think of it as a process where you lift the energy towards the real resonance. And then comes the second photon and gives the remaining energy to match exactly the discrete excitation in the system. But for this to happen, it has to be, this is very unlikely, right? So you need a lot of photons so that this process happens practically instantaneously, and the two photons add up in their energy contribution to excite in this discrete excited state of the molecule. But it's not just the probability that's the problem, it's also a problem. You will see a different spectrum in comparison to single photon adsorption, because we have to consider something else when talking about optical transitions. I mentioned it several times today. We also have certain constraints on when constraints for a transition taking place or not.
Selection rules.
The selection rules, exactly. Yeah.
Momentum and stuff like that.
Pardon?
Selection rules, yeah.
Yeah. You said like angular momentum and stuff. Yeah, this is exactly the point, because our interacting particle, the photon, has an angular momentum of which size? One. It's a boson, like all the particles that communicate a interaction in our particle model or fundamental model of physics. So they have one. This explains the delta L plus minus one. And in the case of two photon adsorption, delta L is not plus minus one, but it is then either 2 or.
But again, please.
Yeah, if delta, so for one photon adsorption, single photon adsorption, delta L is plus minus 1. And for two photon processes, delta L is either 2 or
1.
No?
No?
Zero.
Zero. They have to plus
it can either cancel out or add. So delta L 0 or 2 would be our selection rule, and therefore you see different parts of the spectrum in two photon excitation. So it's actually pretty tricky to find, to offer lasers with the frequency half, so you can in some basically get to this excitation that you're interested in, and also have them with a sufficient intensity, and have two levels communicating that can be excited through a process with delta L plus minus, delta L 2 or 0. But this is a technique that is also giving or offering you the possibility to do Doppler-free spectroscopy. Okay, this is just some details from Hertel-Schulz. I don't have to repeat this. You can. This is not so important. I have it on the screen because I wanted to link it a bit to quantum mechanics. You might have heard about several techniques of how you describe energy levels in approximations. In general, one possibility is perturbational theory. If you have a small perturbation to a Hamiltonian where you know the solutions already, and for two photon excitation, that would be one way to describe it in a quantum mechanics picture, where you say it's the transition from, for example, from 1s to 2s, and you express this in a series expansion in perturbation theory second order as a coupling between all possible states that could lead to the 2s, and your discrete basis of states that you're using in order to get this coupling matrix elements are all the possible excitations from which you can go to the 2s. Yeah, so it's the p excitations, 2p, 3p, and so on. As a basis for your expansion to do perturbational theory. But if you are interested in this in greater detail, I recommend you reading Hertel-Schulz. But as I said, if you do that, it's very helpful to go through the whole book, because Hertel-Schulz builds up on each section and is heavily using references to previous chapters.
Okay, so this is it on Doppler-free spectroscopy. We come to the end. Quickly, please open feedbacker for this question round. The session code today is PBUTB. And I will activate this. This is round 3. Yeah. Must be 2. Yes. 1, 2, and 3. So I activated the 3 questions. I'm reading the first one to you. Which of the following mechanisms cause a homogeneous broadening? First one, Heisenberg uncertainty. Second one, particle collisions. Third one, Doppler effect. Question 2, what is the role of a chopper in saturation spectroscopy? First option, to improve the noise to signal ratio during measurement. Second is to modulate the pump laser, and the third one is to modulate the probe laser. And question number 3, which conditions need to be fulfilled in order to see 2-photon excitation? 4 options, high beam intensity, photons from opposite sides, total photon energy must match the transition, or selection rule, also and or selection rule, delta L plus minus 1.
Maybe one question. What do we call modulate? Just change a beam, or do we mean here change the frequency of a beam? We
No,
say
with modulate, I mean chopping. Because obviously, in order to see a spectrum, we have to go through a certain range and tune both lasers together. But we are chopping one, meaning we modulate the intensity by cutting with a certain given frequency into the beam.
There is frequency, intensity, and some other modulation forms, not just frequency modulation.
Yeah, you can see it this way. You can also think of if you modulate the signal by cutting, you will be able to write this if you do a Fourier transform with different frequencies, right? So this all it's a certain type of modulation, but here it's just if you cut and then you go off and you cut again, then this is happening at the time difference, which is gigantic in comparison to the frequencies of the excitation.
That was actually the
yeah. We're talking about the same. I just wanted to make clear that it's also somehow linked together, right? Because I mean we are in the but you're right, yeah. So it's completely it's not affecting the actual frequency, yeah. Okay, so here we have now 20 votes on 2 and 19 on the last. It's been running for 3 minutes. I think I stop now, and we come to the answers. I see first question is 50% Heisenberg uncertainty, which is correct, 75% particle collisions, which is correct, and the 1/3 still picked Doppler effect, but Doppler effect is not homogeneous because it is dependent on the actual velocity of the atom. So it's not the same for all atoms. It depends on the velocity of a given atom, and therefore we speak of an inhomogeneous broadening in the case of the Doppler effect. Second question, I'm stopping. What's the role of the chopper in saturation spectroscopy? That looks awesome. it improves the signal to noise ratio during the measurement, and it modulates the pump laser. Because if we modulate the pump laser, we will see the effect of saturation on and off, right? And then we can see the difference in the signal. You can also chop the probe laser, but then you don't see the direct difference between saturation and not. You can just distinguish, for example, other types of light sources in your lab from the light source of your probe laser, because then the probe laser is modulated and the other light sources in your room are not. So you can use this to distinguish, but it's not the main source of the problem and not the basics of the principle here in saturation spectroscopy. And then finally, the last question, which conditions need to be fulfilled in order to achieve two-photon excitation? Correct answers are high beam intensity, photons from opposite sides, total photon energy. So these last two, almost 80 and 90% had the first one, 60%. So these were the three correct answers. And the last one, selection volt delta L plus minus 1, is only valid for single photon excitation, we said, because for double photon excitation, since the photon is a bosonic particle, L is 1, 2 photons must be then 0 or 2. And only for one photon, single photon process, it would be delta L plus minus 1. All right. Okay.
May I ask a question?
Sure.
To the results? Why do we need them to be from opposite sides? I understand it why we need it for Doppler getting free access, but I thought, does it really need to be that the photons have to come from different sides to excite just?
No, it doesn't have, it is not necessary to have the excitation, but it is necessary to have a cancellation effect. Because only if they come from opposite sides, you have the compensation of blue and red shift.
Yeah, that's clear. But here was just what is achieved to get a two-photon excitation, because it seems.
I see. Okay, yeah. It's a good point. You're right, because I can obviously also have, and this is a side effect of this technique, I can also have accidentally when scanning, for example, through a frequency range, if I do it with a tunable laser, there will be also the chance to see a two-photon excitation from two photons coming from the same side. And this gives you very low intensity peaks shifted also off the real transition, so you can identify it pretty easily. In most cases, however, you're right, it is a problem. And the one way to compensate this is to use polarized light, because you also have a constraint on the polarization. You polarize one left and the other one right, and then you have the cancellation effect, and only for cancellation left and right you will have the transition allowed. And if two photons coming from the same side, they don't sum up in this polarization quantum number. They don't give you 0, and is not allowed. So you can use polarization, circular polarization of your light coming from left and right to completely reduce these side peaks that will occur.
But this question was really targeting the thought process of how do we get the cancellation of our Doppler effect also in this sense.
Yeah.
Because we require.
Yeah. No, but it's a good point. So I'm glad you asked this. You can read up on it in Hertel-Schulz, where they give a bit more details on this, on the circular polarization technique.
Maybe. I mean, if somebody else has a question, please interrupt me first. I just was wondering about, we mentioned this now multiple times about the homogeneous effect and the inhomogeneous effect. I see why these effects are the ones with homogeneous and one inhomogeneous, but how would I not see this really in a measurement, that the one is an inhomogeneous effect, the other one is an homogeneous effect? So, or do I just say, with this method, I eliminate the Doppler effect and not the other ones? Or is there some way of distinguishing?
So, yeah. So it doesn't really lead to differences in how the spectrum is shaped in principle, except for the fact that different mechanisms might create a different type of line shape, as we discussed. We have the natural shape, Lorentzian, and we have this Gaussian broadening. But it is simply a term that refers to how it is affecting the ensemble of particles that you have sitting in your cell. It is either something that is the same for all the particles and can be explained through like the usual thermodynamic ingredients, so pressure and temperature, or if it's inhomogeneous, there is a dependence basically on how you look into your system. So an inhomogeneous broadening is a broadening that depends on how you set up your experimental arrangement of lasers with respect to, for example, the beam, right? So this is the idea. I wouldn't see it this way. It's just one way of distinguishing, which doesn't really help you with the final spectrum itself, but it helps you with telling how this is related to features of your experiment. Because if there is some dependence on the actual position of lasers and molecular beams, it is obviously an inhomogeneous type of broadening that you are dealing with. So, are there any further questions? If not, I would stop here and thank you all for participating. Again, if there are any questions, you can also write me, and I will see you all again next week on Tuesday. Thank you and have a good week. Bye-bye.
Bye.